So the correction, I mean, which I am calling as a, the betas correction, we call it as a backward propagation and forward propagation. So the backward propagation and forward propagation, so this is what I was referring that. A backward propagation is nothing but for each weight synapse, multiply its output delta input activation function to get the gradient. Of course, I will tell you what does this mean, but at least what I'm trying to explain you is whenever there is a I mean, this is assuming that input layer and output layer or something. Sorry, this is initial layer and then the next layer. The corrections will happen this side. First, it will correct the most recent layer from the output, and then it will go one layer before and one layer before. That's how the corrections will be done for your betas. And this process, we call it as a backward propagation. So when I say backward propagation, that is the one of the common method used in the industry to correct, because that's the most optimal way of doing that. And now when it comes to the backward propagation, I think this is what I was referring that. Now let's come to the optimization here. The optimization is nothing but how the corrections will happen. These corrections will happen in such a way that the output will give you the maximum accuracy. That is the idea. So in this case, if you look at this, suppose if I'm taking a neural network with the sigmoid as a activation function. Each neuron is a one kind of a logistic regression. Correct. Suppose if I have 10 neurons, there's nothing but 10 logistic regressions. So basically, you want to minimize the overall error at all the 10 models. So that's the reason it's a summation of all the cost functions. So that's what we want to minimize it. Suppose in a simple logistic regression, you have one cost function. And if you have collection of logistic regressions, in this case, these are multiple logistic regressions we are performing. Each neuron is one logistic regression, right? Correct or not? If I'm taking a sigmoid curve, each neuron is one logistic regression. That means in each neuron wise, you need to estimate the betas. Do you agree with me? So basically, you are collecting all the betas and all the logistic regression, and I'm trying to minimize the overall error part by correcting the betas simultaneously. So of course, the cost function is slightly heavier in this case because here what happened is you are taking a collection of logistic regressions. If I take a sigmoid curve as this one, for example, if I'm taking as a linear activation function, this is nothing but multiple linear regressions. Make sense or not? So that is the fundamental. Yeah.
Can you go to the previous slide, 23?
Yeah.
Can you just explain it once more?
So what I was saying is, of course, we did not discuss this cost function for logistic regression. What I'm saying is, suppose if I have my logistic regression, this is a one cost function. Assuming that I'm taking an activation function is sigmoid curve. Now in my neural network, suppose if I have 10 neurons. So when I'm doing a 10 neurons, what does that mean? You are performing a logistic regression 10 times. Correct or not?
Yes.
So if I take a single neuron, so this is my activation function. If I take a collection of neurons, my activation function will be a summation of all the logistic regressions. So that time, if I'm taking one single neuron, this is my activation function. If I take a multiple neurons, that means my activation function something looks like this. So this is, obviously, you are simultaneously minimizing or maximizing what is the activation function. Sorry, maximizing or minimizing your objective function. So by the way, this is what we call as a MLE. MLE is nothing but maximum likelihood estimation. So MLE use there is a estimation called minus log likelihood. Minus log likelihood will be calculated in this manner. So basically, you are calculating the maximum likelihood, which is same as a minimizing minus log likelihood. Don't worry about that. When I'm explaining that log likelihood, I will explain that. But at this point of time, assuming that this is my, I'm minimizing this function. So now if I talk about one single logistic regression, you are minimizing this one. When you are talking about a collection of logistic regression, you need to minimize this one. This is how it works. Does that make sense?
Yes.
Okay, perfect. So that is the underlying objective. Optimization works behind the scenes. Okay.
Chandra, I have a question.
Yeah.
So you said backward propagation is when we are adjusting the weights and betas, right? To make, I mean, to get the correct classification. What is forward propagation? I mean, if so, once the weights are updated, then we're calculating again.
Correct. So that means that when it's adjusting the betas is from right side to left side.
Correct.
So for example, by assuming the output is this value, so to achieve this value, first we will make sure that the betas will be adjusted properly. And that betas will give me the output, whatever my target output. To achieve this output, and you are taking the input as some value like this. So to get this input, you will adjust this betas in such a way that the value of input will be something like this, and you will get the output is something like this. So that means that the adjustments what we are doing is, okay, this is my most recent layer, and this is my second most recent layer. I will adjust the betas between these two things as a first, and then I will try to adjust this betas in such a way that the assumed outputs you will achieve it.
Okay.
This is what we call as a backward propagation.
And what is forward propagation then, Chandra?
Forward propagation is, I'm saying that first you will adjust the betas this one, and then you will adjust the betas this one, and then you will get the final output. That is the left to right, the adjustment of betas.
After the first misclassified iteration.
Yes, once you get the iteration is done, then you are adjusting the betas left to right.
Okay, then how do I know if I want to go by forward or backward propagation?
Generally, we use forward propagation will take more time, because end of the day, here what we are doing in the backward propagation is, we are doing that, we are trying to adjust closest value for my output value. So that means that you are sure with this part. And in order to achieve the best values, you will also be sure, you will sure with this middle layer what we want to achieve, and for that you will try to adjust this one. So the backward propagation is most appropriate. So in your neural networks, in most of the scenarios, in majority of scenarios, you will use backward propagation, because the backward propagation is relatively quicker and easier to learn. Because easier to learn means easy to less number of iterations itself you will able to achieve it. We don't use forward propagation. So just forward propagation is a method to understand what is the backward and forward. But in the work perspective, or in the algorithm perspective, it will use backward propagation. Does that make sense? Okay, guys, so now you're clear with what is a neural network and how the neural net will be created, and how the corrections of betas happens, one iteration to another iterations. So now the question is, how many iterations we should follow? So either this might be, how many iterations it might be. There are two ways. If the solution is converges. What do you mean solution is converges? Means if there is no change in betas, you can say that there is a very minimal change betas between last iteration to current iteration. What does that mean? Okay, the last iteration is my beta value is 0.0 0.499, for example, and after next iteration, it's you got as a 0.4999. Maybe 0.1, something like that you got. So that means the difference between this side, I mean, this is the previous iteration. This is the current iteration. If you see, the difference is how much? 0.0001, right? Correct or not? So if that is very minimal, you don't need to do the iteration again. That's what it means that the solution is converges. Or in sometimes the solution is not converged, you can also restrict. Okay, you can define my minimum number of iterations equal to 100. So it will stop at 100. Okay. So the solution, you can also specify how much you want to see the difference. Now, if you see that the difference is less than that, that is what we call as a tolerance. What is the tolerance? The tolerance is something which is nothing but the current iteration to previous iteration. The difference is called as tolerance. The tolerance is, for example, if I specify my tolerance is less than 0.001, then it will stop it. So I mean to say that the difference between the previous iteration and current iteration is hardly difference. I mean, is less than 0.01, then I'm stopping it. So this is also one kind of a parameter when you are supplying a neural network. So are you clear on this one? How many iterations? Now, in terms of the accuracy, so accuracy is similar to what we have done in the past. So what is the things? What are the things? The accuracy is like regression metrics, classification metrics, exactly the same. There is no difference as such. So this is what exactly a quick understanding about neural networks. But when we are implementing in Python, so implementation of in Python is there are multiple modules we have it. One is sklearn, also you can use it. And there are a couple of other modules also, which we are not going to cover part of our course. But there are modules like Keras, TF-Learn, and Piano. These are also different modules you have it, different packages we have it. This is what TensorFlow network, Keras network, Piano. So these are all are different packages which you can also use it. But here we are using scikit-learn. Under that, a neural network is the module you have it. Under that, you have a MLP. What is MLP? A multi-level perceptron. So you will use this multi-level perceptron to design the neural network. So when you are designing the neural network, what are the parameters we need to supply? The minimum parameters you need to supply is network. The network is nothing but what? Number of layers. And each layer, how many neurons? And if you want to add, learning rate or a threshold value or a tolerance, these are all you can supply it. If you don't supply also, it will take by default values. Does that make sense? Okay, perfect. So now let's do this implementation part.
Chandra, just one quick question. So when we can implement neural networks with sklearn, I mean, what advantage the other packages like Keras and TensorFlow give us?
Okay, so most of these things, for example, advantages with the other things. So basically, the neural networks, I told you, it's a shallow neural networks. Shallow neural networks. Shallow neural networks means with one layer. And if you have a multi-layer, so when it's a multi-layer is nothing but this is what we call as a deep neural networks. So when it's a deep neural networks, etc., there is some kind of a customizations. What is the customizations? You can do that. One is one customization is okay. Each neuron, I want to select a one activation function. Right now, what happened for everything you are you are doing a activation function is same. But now I want to do some kind of a special, one customization function for each layer. Okay, I have two layers. Okay, layer one, I want to use a sigmoid. Layer two, I want to use some other activation function. So that is some kind of a customization if I want to do. The current scikit-learn won't support. And not only that, there are some kind of a deep neural network. There are different neural networks we have it. Like there are a couple of other things like CNN and RNN. And CNN means convolutional neural network. And RNN means recurrent neural network. So under the recurrent also there are multiple methods like LSTM, long short term memory neural networks, etc. Like this, there are different neural networks based on some kind of a mechanism of estimation of your weights and calculation, etc. Right now, the estimation we used simple error function and corrections, but the estimation process can be a different manner. So that's the kind of scenario. There are some more additional algorithms, based on the neural network, which is, implemented. All these things comes under deep learning. Deep learning is nothing but extension of neural network. Instead of one single layer, you are doing a multiple layers, and the estimation process and the customization, etc. you will not have with the shallow neural networks. For a shallow neural network, scikit-learn works well, but other networks, the deep learning perspective, you have the TF-learn, TensorFlow, as well as Keras will be having some kind of additional features which you can customize it better. And not only that, this deep learning requires a lot of computational process, and you need to make sure that it should be quicker. Some kind of a parallelization, etc. You want to do that. So the current sklearn is not supporting the parallelization, but whereas the deep learning, especially modules like TensorFlow or Keras, they have some more advantage in terms of the parallelization, etc. So these are the few advantages you have with the other packages. Of course, Theano is not so popular, but yes, these two are popular. Out of that, the TensorFlow is popular because TensorFlow is built on top of Keras only, with more features. So if you know Keras well, of course, TensorFlow and Keras is similar. Keras is little, basically you can say the vanilla version, and the TF-learn is more features on. This is built on top of Keras only. End of the day, the underlying TensorFlow works based on the Keras only. Is that clear?
Yeah, Chandra, one question.
Yeah.
In ANN, how can we construct regression equation? And for the classification, how can we came to know what will be my cutoff?
I did not follow you. So linear regression, when there is no regression equation, you will not able to get it here.
Yeah. So how can we construct regression equation with if you are working in ANN?
So guys, one important thing is ANN and this one, random forest or a bagging or a boosting, and these kind of things you will not able to get explicit. You will not able to get explicit mathematical equations for each, for the model. So that is the one challenge you have. This is what I was, explaining in the, when we are explaining in the neural, when we are explaining about machine learning, there is a trade-off we are taking. What is the trade-off? The explanatory power. The explanatory power means you are unable to explain in the mathematical form. Okay. So here you will not able to get explicit equation. But whereas a linear regression, logistic regression, simple decision trees, and there you will get the rules or something, right? Even in KNN also you will not able to get it, right? There is no mathematical equation as such. Even Naive Bayes also there is no mathematical equation, only you will have a probabilities, right? And SVM you have a decision boundary. There is nothing but that line you can at least talk about. But here you cannot talk about that.
Okay.
Right. So these are the things works with only machines. You will not able to implement a static solution on the implementation stage. Perfect. So whereas a linear, a logistic, or GLM models, and what is the other one? SVM and decision trees. Either you can get a mathematical equation or a rules to implement the solution, or maybe from the model. Perfect, guys. So now you're clear what is the neural network, how we can implement, etc. Okay, now what we will do is we will implement all these 4 things: KNN, Naive Bayes, SVM, and ANN. And as I said that KNN and Naive Bayes, these are all non-parametric methods. And here parametric methods. Okay, so when I say non-parametric, you will not have an optimization as such, because there you will not have an optimization like a cost function or etc. So here, what is your thing we need to find out? The K value. Here there is no tuning parameters. What is the tuning parameters? In this case, tuning parameter is K. And here no tuning parameters. Only tuning parameters, if you think about it, only parameters you may think about is what type of Naive Bayes technique. What is the type of Naive Bayes I told you in the last class? One is Gaussian, one is a Bernoulli, one is a multinomial. You remember, Gaussian is nothing but, I told you Gaussian can work when if the data have, of course, data have a continuous variables, and of course follows normal. And Bernoulli works categorical variables. You can say it's a dummy variables. And multinomial, a discrete kind of a variables. Correct? So what about SVM tuning parameters? Yeah, for this SVM tuning parameters is what is the tuning parameters? type of kernel, and learning rate. And what is the other two things I will explain that what is a gamma and what is a C value. So these are the couple of things. And ANN, what is the tuning parameters? ANN, okay, number of layers, number of neurons in each layer, learning rate, activation function, threshold, and tolerance, and number of iterations in case if you want to use that. So these are the different parameters for the N. Is that make sense? Okay. So anyway, I'm going to use all of this scikit-learn only. sklearn, we can use it. There is no issue. We will talk about that. But before that, I also want to quickly talk about the balance and imbalance data. What is the balance and imbalance data, guys? Suppose if you have, this works when you have a categorical, classification problem. This is applicable to classification problems. What is the classification problems applicability? So suppose your y variable is a multinomial variable, like for example, high risk, medium risk, and low risk. Okay. Suppose your data having 100% data, under that 20% or maybe 30%, 20% is here, and 40%, 50% is here, 30% is here. So what does that mean? All these are not in a same scale, same proportion of observations. If I have 100%, suppose this is 33.3%, this is a 33.3%, and 33.4%, suppose. And this is what basically, this is a imbalanced data, this is a balanced data. So balanced data is something, I'm saying that all of them are having a equal proportions. And imbalanced data, some of the categories in y variable having a higher proportion or lower proportion. And similarly, if I have y variable, my ones and zeros. So my total is 100%, and and of course you want to use it like this. And of course, in this case, suppose I have 20% data, 80% of data here. Here is 50% and 50% of data. So if both of them are having a 50%, 50%, I'm calling as a balanced data. If the imbalanced data, we'll do that. So this is what balance imbalance. So why I'm talking about this one is, most of scenarios, like for example, SVM, or for example, random forest, for example, bagging or boosting, decision trees, right? ANN. What happened is, by default, what you do is you take a threshold value is 0.5. What is the 0.5? Threshold value means the probability value, whatever the output you get greater than 0.5, I'm calling as a 1, less than 0.5, I'm calling as a 0. So this threshold value works well if my data is balanced data. If the data is balanced data, all these techniques you don't need, you can directly get the outputs as a target variable as 1, 0 variables. But if my imbalanced data, you have it, you cannot use threshold value as a 0.5. For example, in logistic regression, what did we do? We calculate the probabilities, and from the probabilities, what did we do? We identified the cutoff. So that is the cutoff is threshold. Are you clear now? So if it is a balanced data, the threshold value is 0.5 is okay. If it is an imbalanced data, the threshold value cannot be used as it is. So that is something which we need to handle. Generally what we do is whenever you are applying these algorithms, you need to be a little bit careful. Is the data is a balanced data or imbalanced data? If it is a balanced data, you don't need to worry about. You can directly get the outputs as a target variable. But is it balance? If it is a balanced data, you can directly get it. If it is imbalanced data, you need to calculate the probabilities and get the cutoff. This is the method 1. But some of the techniques won't consider. Suppose, for example, ANN, the output you will always take as a 0.5. Then otherwise, you can also use the threshold value as a tuning parameter. But otherwise, what you can also do is convert, imbalanced data into balanced data. How will you convert? This is the place, you remember, we have a concept called oversampling and undersampling. Or there is a mixed kind of a thing. So what is oversampling and undersampling? For example, let's take this example. This is imbalanced data. Suppose if I take this data, and what happened, my 1C is 20%, my 0C is 80%. So this is not a balanced data, right? It's imbalanced data. So in this kind of situations, what we can take is, we will take 20% of data as it is from ones. That means all the ones you have, for example, you have 1000 observations, 200 observations are ones. Take all the ones, that is nothing but 200 observations. And remaining 200 observations, we will take a random sample from this one. So from the 80%, we will choose 200 observations. But from the 800 observations, you will take a random sample of 20%. Then it will be a balanced data. But the only thing is, 40% of the data you are finally choosing out of this. But you are making sure that this is a 20%, 20%, it's a balanced data. So this is the methodology we call it as an undersampling. Okay, then what is a oversampling? So you will take 80% of this data, and this one you will take a duplicates of that ones. What is the duplicates of ones? Okay, this 20% you will repeat 4 times. Then 4 times of ones. That means you will create a duplicates of this one, and you will also create this. This is what, in this case, what happened? Now 160% of data you will have it. I understand. This is what we call it as a oversampling or mixed sampling. Mixed means hybrid. Hybrid means you will take a this one as well as this one. So what we will do is, we will bring this one is 50%, and this one also you can say 50%. How? From 80% I can reduce it to, I can take a 50% of sample, 500 observations. And this one I can multiply with 2.5 times, I will get the 50%. So this is what we call it as a hybrid sample. Okay, what I'm saying is, for example, instead of this one, let's talk about the same thing in a better manner. So what I'm saying is, I need to get 100%, equal proportion of ones and equal proportion of zeros. For example, I have 1000 observations, and 200 observations are here, and 800 observations are here. Okay. And what I'm saying is my undersampling is I'm taking all the 200 sample from the ones, and in this case I'm selecting the 200 observations, so that 50%, 50% you will now able to see that. I mean 20%, 20%. The oversampling is I'm saying that take 800 observations and here 800 observations. What does that mean, 800 observations? You have only 200 observations. How will you make 800 observations? So you are repeating the same sample and again 4 times. That means you are taking the 4 times duplicates. And the mixed is nothing but what? Bring it 500 and bring it 500. So how will you bring it 500? Take a sample of this one and multiply, I mean take duplicates of 2.5 times. This is what? The hybrid or a mixed sample. Are you clear now? So this is the basically, there is a module in Python, we have it, imbalance module. There is a module called IMB, imbalance is the module, you have it. So that module will help you to perform undersampling, oversampling, mixed sampling, whatever you want to do that, you can do. Why do we need this is, because we want to take it as a 0.5 as a cutoff, because the threshold. That is one reason. The second reason is, a lot of times, you have data. Why do we need to take care of, the imbalanced data? First reason could be, the reason one is, by default, taking the cutoff is 0.5. Okay, so that means the output you will get it, that one. The second one is by default, I mean, some of the data have very less number of ones. Like for example, fraud data. So generally the percentage of fraud events will be very less, right? So you might have ones are very high. Ones are maybe you have the total 1000 data. In the total 1000 data, ones probably you got as a 10, and the zeros you got as a 990. So in this case, will you able to build the model with less, 10 observations of ones? It's highly difficult to get accuracy. So this is the place we'll also see oversampling, undersampling, and mixed samplings. Right? This is the another reason.
So Chandra, I have a question.
Yeah.
So in the oversampling, we took like 4 times of 200, right? But it's the similar observation. I mean, the model will learn the same thing again and again. So
similar observations, but I'm saying that the behavior is same.
What do you mean by behavior is same?
See, if the customer is a bad customer, I'm saying that the customer is the behavior of bad customers is similar. That is the one of the assumption I'm taking, and that's what I'm trying to do oversampling.
Okay, but what I'm saying is that with same observations in my data, right?
Correct. Same observations you will have it.
So how will it add value to my model learning actually?
It is not adding a value. It is, end of the day, you remember my sum of ones is same as my sum of probabilities.
Correct.
Right. If you are having a very less number of ones, it's very difficult to differentiate zeros and ones. Now you are having a more number of ones, and I'm able to differentiate zeros and ones because the probability value, will get higher side.
Okay. Okay, now I got it. Thank you.
Yeah. So this is the underlying concept about the balance and imbalance kind of thing. Does that make sense?
Yeah, Chandra.
Yeah.
Yeah, it makes sense for balance and imbalance data. So I have one scenario. Suppose I'm going to create a model. For instance, say I'm creating a logistic regression model, but my data is like, suppose it's a 50 lakh. So, and if you want to do cross validation, logistic regression, so it's very computational expensive, and it will take more time. Like if you run cross validation like a k-fold model, so it will go 5 hours or 6 hours. So it's very difficult to do on a simple machine. So if I want to create a model in my local machine, so what approach should we take? I don't want to create a model based on a 50 lakhs record.
Okay. So generally, what we do if the huge amount of data is there, which you can't use your local machine. So what generally I do is, if I apply a multiple models or multiple tuning parameters or a cross validations, it will be highly time consuming task. So generally what we do is we take a 50 lakhs records and probably you take a 10% of sample, which is nothing but a 5 lakh records. Okay, and build a model on the tuning parameters, etc. There you will get approximate tuning parameter values. For example, I'm getting the tuning parameter of, so initially we start with the grid search of 10. Now I can, for example, grid search of 10 on the sample data. Based on that, you will get the closest value. Correct. So once you identify what is the right set of tuning parameters and rerun, just taking a plus or minus 1 of, it's closer to those tuning parameters, just run on the entire data. Even that is also not supporting.
Yeah, Chandra, one question. Just you just said we need to take 10% of the data. So if you are taking with the help of a sample function, and my data has 0 and 1. For instance, for the credit card, we are predicting who will be default and who will not be default. So there is a one parameter which having 0 and 1 value. Suppose we are taking 10% of the sample. So what is the surety that 10% sample will have the equal amount of 0 or 1? It may be possible 10% data having only zeros or 10% of the sample having only 1. So how we can make sure that 10% data having the same amount of zeros and 1?
Okay, see, the random sampling is something when we are doing, I think that will take care of your randomization. So I think when you're taking the randomization, you will get approximate values of, for example, your Y is having, 10% of ones, your random sample of 10% also will have approximately close to 10%. It may not be exactly 10%, but you may not get a close to sample of 10%. Or if you not sure with that, and we also have another mechanism called stratified sampling. What is stratified sampling? Okay, you have the data of ones, you have the data of zeros. Take a 10% of ones out of ones and 10% of zeros out of zeros. That is a stratified sampling. So my understanding is if you perform a random sample of 50 lakhs, 10%, if you take it, still you will get it 10%. It may not be 100% 10%. Close to 10% you will get it. But if you want to make sure that 10%, I want to make sure that get in my sample, probably then you can try with the stratified sampling. Does that make sense?
Okay. But you just told that if you take the 10% sample, it will the proportion it will try to maintain.
Yes.
But I have done one. I was building one of the model, so such kind of scenario was not there. I have taken.
I think probably you did not do random sampling. Maybe I don't know what sampling you used it there, but a random sampling is something if you're doing, it will maintain the proportions.
Okay, maybe I was not doing the random sampling.
Yeah.
Okay.
Okay, so that is the sampling part. Now let's talk about the optimization what did we do optimization, guys? Guys, before that, you want to take a quick 5 minutes break? Okay, let's take right now 12:05. By 12:15, we should be here. Okay, guys. So in terms of the optimization, so the optimization is, if you remember, we discussed about two things in the last session. I mean, not last session, I mean earlier. Every business problem converted into statistical problems. That statistical problem will be converted into optimization problem. You remember that? This is the discussion we have done it. Then we will solve the optimization problem. And this optimization problem solution will be converted into stats solution, and that stats solution will be converted into business solution. Correct? Am I right or wrong? So now, what is this optimization problem? So the optimization problem is nothing but everything will be converted into a maximizing or a minimizing an objective function with constraints or without constraints, whatever it is. A simple example is, in our case, if you think about a linear regression, what did we do in the linear regression? You are minimizing sum of squares of error. Of course, there is no constraints in that. What is sum of squares of error? For example, your yi is your y variable, your xi is a x variable. What we are doing that? Minimizing sum of squares of error is nothing but what? Your yi minus a beta 1 times of xi minus constant whole square, and take the summation, sum of squares of error. So if you look at this one, what is unknowns in this? Beta and constant. You know your yi, you know your xi. Correct or not? So basically solving optimization problem, nothing but finding the values of unknowns. What is that thing? Nothing but finding the values of beta and constant in this case. Are you clear? So solving optimization problem, in this case, how will you solve this optimization problem? So this is the place we have a optimization algorithms. What are the optimization algorithms we have? It is, one is a gradient descent algorithm. And the second one is, of course, similar to this one, is stochastic gradient descent algorithm. Mini gradient is also called as a batch wise. This is called as a observation wise. These are the three variations of algorithm, but there are so many algorithms are there. But in our data science perspective, we will use gradient descent algorithms, or a stochastic gradient descent algorithm, or a mini gradient algorithm. So these are the different variations in the gradient descent. Okay, anyway, so the gradient descent algorithm we always use for a minimization problem. So all these three things which I was referring, that all these are solving minimization problems. Okay, you might have a solving maximization problems also can be possible. So there you have a gradient ascent algorithms. Gradient ascent algorithms. I mean, this is just similar, only thing is the opposite. And similarly, stochastic gradient ascent algorithm, and instead of mini gradient you will have a, mini gradient only, you will have a ascent algorithm. So this is something, maximization problems you will solve with this. Minimization problems will solve with this. Are you clear now? Okay. So now what is this gradient descent algorithm? The gradient descent algorithm is something like this. So first, the objective function. Objective function is nothing but we also use a cost function. Okay. So what is this objective function in our case in a linear regression? We are saying that sum of y minus beta x plus constant whole square, right? So this is some, suppose if I talk about this one, this is ax plus b whole square kind of a formula. Am I correct or not? Ax plus b whole square. This is the kind of a formula, right? I mean, if you look at beta 1 is x, you can consider, and yi and c is, assuming that constant, and this is xi is nothing but a. Can I say that this is ax plus b whole square? What I'm saying is I'm just modifying this one in such a way that yi minus c is a constant. Okay, so that is we call it as a b. B is nothing but yi minus c. And what is a? A is nothing but xi. Assuming that, then that time where xc is nothing but your beta 1, assuming that, just assuming that. So can I say that this one is something similar to this? Okay, now any kind of a quadratic function, a quadratic polynomial, the quadratic polynomial you always have a positive values. Quadratic values has positive values. Now, whenever I'm talking about a minimization of sum of squares of error, what is that means? For a combination of a beta 1 and a constant, whichever value of cost function, whichever combination of beta 1 and constant, cost function will give minimum value. Correct? So that means that, can I say that my betas and my cost function value, suppose if I'm taking a beta 1 equal to 1 and a constant equal to 0, I will get one cost value, for example 300. And beta 1 equal to 2 and cost equal to 2, and say I have a 150 value, and something like this. For every combination I can get these values, and whichever combination gives me a minimum value, can I say that is my best value? That is the interpretation perspective we are doing. But if I'm looking at a cost function is something like a simple function. This function, can I write some kind of a equation? Suppose if I look at the polynomial function, the polynomial function is always like this. For example, my betas, negative values also will have a positive values, and positive values also will have a negative values. So whichever values of, assuming that this is my betas and this is my cost function value. Cost function means the objective function. So for example, corresponding beta values, I can calculate my cost value, like for example 300, 150 or something, and I can say that this is the value, and which is the least value. So that means corresponding beta, this is my minimum value, I got it. So that means that if the polynomial is there, I can find out a minimum value, right? This is my solution, right? But how to get the solution? So that means I cannot do for every combination like this. I can that means infinite possible combinations I will get it. So that means that to make it quicker, make it faster, what is the best way to do? That is what the gradient descent algorithm will tells me that. Are you clear? So now what is the gradient descent? Suppose what it will do is, an algorithm perspective, it will start with some value. What is the some value? For example, you are starting with a value called beta equal to, for example, 2, assuming that 2. Okay, for a 2, what is my cost function? Okay, for example, corresponding to, you got a cost function is like this. Mahesh, that is what I'm explaining, guys. So whichever gives you minimum value, that is fine. But how to identify a best combination? How to identify a best combination? You know, that means that if I have infinite possible options, do we need to create an infinite number of times and calculate the value? That means it's infinite loop. That means how can we ensure that, for example, you take 100 combinations, but how can we ensure that that is the minimum value? Correct or not? So that's the place this algorithm play a role. What I'm trying to say is, assuming that my polynomial function cost function is something like this, my polynomial cost function always have only one minimum value, right? Because it's always have a minimum value is 1. Suppose if polynomial function, suppose order of 2, that always have this kind of a functional form. I mean, this kind of a curve you will get it. Correct or not? So that means that if I'm taking randomly one value of beta, suppose randomly one value of beta, that means that corresponding beta you can calculate the, my cost function. So assuming that this is my cost function, you got it as 300. Okay, you got a 300 corresponding my beta equal to 2 and constant is something. Okay, now what I'm trying to do is, suppose I change my beta value. Okay, the beta value is my value is increased. My beta value is increased. My instead of, okay, assuming that this is a 1 and my value is increased to 2. So from 2, that means that corresponding to also I can calculate my sum of squares of error. For this betas also I can calculate sum of squares of error. So assuming that I got 150. So what does that mean? It means that, it reduced the error from 300 to 150. By increasing the value, it has got the 300 to 150. So if it is increasing, then it is fine. But some reason your B1 equal to 2 and your cost value is increased to, suppose 320. Your cost value is increased to 320. So that means that what is my solution can be? My solution cannot be beta 1 equal to 2. Why? By increasing the value of beta, you are getting the higher value of cost function. That means that may not be a solution. So then what we will do, we will see that a lower side of the beta. So instead of increasing the beta, you will try to reduce the beta. Then you will see what is the solution. Yes, beta values and cost value. Of course, to explain you, I'm talking about here. But what I'm saying is, I'm saying that if I'm randomly choose my beta value, that is my initial solution. That is my initial cost value is 300. By increasing the beta, I'm getting there are two options, right? Either you will get a higher value of my previous cost or lower value of my previous cost. If you are getting a lower value of previous cost, then I will choose this as a solution. Solution means the next iteration. My next iteration of beta will be beta 1 equal to 2 and constant equal to 2. But some reason you are getting a higher than the earlier cost. Then what happened? That means this cannot be a solution. Then what we will do? The solution can be a lesser than, the first one. That means the beta 1, instead of increasing the value, we will reduce the beta 1. Okay, now beta 1 equal to 1. Instead of that, what will you take? Beta 1 equal to 0.9. So indirectly what I'm saying is, by increasing or decreasing the beta, if you are getting the lower value of cost, that's how you will move the direction. So in this case, assuming that my second iteration gave me 150, which is a reduced. So that means that it is decreased. Now my new solution is what? My second iteration is beta 1 equal to 2 and c equal to t. So now again I will look at, by increasing the value of beta, am I reducing my cost or not? By increasing the value of beta, am I reducing my cost or not? For example, beta 1 equal to 3 and you reduce it from 150 to 120. Now my new iteration will be what? My new iteration will be what? Beta 1 equal to 3. Of course, see, just for example, when I say beta means you are talking about both beta and constant. I'm not saying that just for example purpose I was talking about is a one parameter because it will be easy for you to show in the output. But when I'm referring to the betas, I'm referring to the including constant. So here I'm calling it as a constant, but there it generally we call it as a beta naught. Beta naught is nothing but beta. So indirectly what I'm saying is, by increasing the value of beta, am I reducing the beta? Am I reducing the cost or not? If you are reducing the cost, my new solution, my new values of beta will be that. Otherwise, what happened? You will not go up, you will go down. So yeah, so my new iteration I got is first see guys, what I'm saying is, assuming that my first iteration, okay, for the time being, I'm taking a simple single beta. Okay, beta. So beta equal to 2, beta equal to 1, I got 300 as a cost value. Now beta equal to 2, I got 150 as a cost. Suppose my beta equal to 3, what is my cost? Suppose 170, for example. Now what happened? Is it increased from this to this? So that means that beta 3 cannot be a solution. Now the solution will be between what? 2 and 3. Sorry, not 2 and 3, 1 and 2. So now instead of 2, you will reduce the beta. So now what we will do? Beta equal to 1.9. So suppose 1.9. Suppose if you are getting a beta, I mean the cost is, for example, 145. Now my solution is basically what? 1.9. Now again here I need to look at then again look at beta equal to 1.8. Now am I getting the value of cost is reducing, for example, assuming that it's a 142, it's reduced further. Then again beta equal to 1.7. Now what happened? Assuming that there is a cost is increased. Now what happened? This cannot be a solution. Now what we will do? It will increase. So beta equal to 1.75. And now suppose if it is a decreasing 142.5. So I can reach convergence, the solution whichever is minimum. Yes or no? So until there is no change in the beta. See, from what happened, we started with 1 and now we reached 1.75. Now after 1.75, if I'm changing my betas, if there is not change in the cost, that means we will not change anything in the beta, right? So that means this process we will change until there is no change in the cost function, cost value. Until there is no change in the cost value, we will continue the iterations. We'll continue the iteration. That means that we'll continue change the beta values. If there is no change in that, so that is what if there is no change in the cost, that means your solution is converged. Does that make sense? So this is what we call it as a gradient descent algorithm. So we are looking at descent in what? Error. Descent in cost. Right? Which values of betas will give me a descent in the cost? So that means I am looking at the solution, whichever is giving me a descent. whichever is giving a highest, then I will not go for that. That means I'm completely ignoring that solution, right? So this is the way, in this case, once we ignore the solution, suppose once we ignore the beta equal to 3, I will never go towards that. I never go towards that. So once we ignore the solution, we will ignore completely for the entire process. We'll ignore it for a complete process. Does it make sense now? Are you clear? Online guys, does this make sense? Okay, this is what gradient descent algorithm. So if I look at gradient descent algorithm, what we are doing is we are taking the sum of squares of error, the total error, not only a single observation error. This is we are taking a total error, and for the total error, you are calculating the betas. When we are referring to the stochastic gradient, what is the difference is stochastic.
Chandra, I have a question. So
yeah,
what do you mean by total error? I mean sum of square of errors, and then how you changing the beta? I did not get your last line. What you said?
No, I could not follow you.
So you said a last line, right? That we are checking this in total error. So what do you exactly mean by that?
Total error means you have your yi, you have your xi. I mean, that's nothing but yi means xi means, okay, suppose serial number, for example, 1, 2, 3, 4, 5, 6, etc. Suppose I have 5 observations. What 5 observation is? For example, your 300, 200, 150, 190, 320, something like that. And xi is, for example, 30, 20, 15, 25, 26, 32, something like that. And you are saying that your y equal to beta 1 x1 plus constant. Suppose assuming that my beta 1 is, in this case, for example, beta 1 equal to 1 and constant equal to 2. Now what is your value will be? Suppose beta 1 is nothing but 300, sorry, 1 is nothing but 30 plus 2. 32 you will get the value, right? 1 into 30 plus 2. Okay, assuming that this is a 270 or 230 or 250 or 260 and 310. So, and this is what you got it. And what is your error? Sum of squares of errors. So first you need to take a square of error. This is nothing but this minus this. And your sum of squares of error is nothing but SSE. Is total error is sum of all. Is that case? So for a beta 1 equal to 1, c equal to 2, my SSE value is be this one, this much. So now again, by increasing beta 1 equal to 2 and beta c equal to 2, now what is my value will be? My y equal to 2 times of x1 plus constant, right? So that is nothing but what is my value? 2 times of this one plus equal to 2 and beta c equal to 2. Now what is my value will be? My y equal to 2 times of x1 plus constant, right? So that is nothing but what is my value? 2 times of this one plus 2, right? Now what is my error? Correct? Oh, sorry. Okay, now my error is it increased or decreased by taking the value? It's increased. So that means this cannot be a solution. Now what can be the solution? The solution can be lesser than this value. So lesser than this value means, that means I will not try any more greater than 2 of beta value. What I will try? I will try less than beta 1. Beta 1 equal to, now what I will do, beta 1 equal to 0.9 and C equal to, for example, I mean assuming that 2. So now I can get the values now. Now I can see that. So like this will work, guys. So that is what my cost is changing by different things. For example, if this is the solution, I will not include the solution. Then I will reduce my next iteration. I will look for whichever betas gives me a lower side of the value.
So Chandra, how was the cost? Can you go back to the table on the left? So cost you're taking as constant.
No, cost is not constant. Cost is nothing but your SSE. Your SSE is cost. Cost is nothing but, that's what I said, objective function or cost function.
Okay. So your last line, you were saying that we are looking at error as a whole, not an individual error. So
yes, not as an individual error. So this is what we are calling as a gradient descent. Stochastic gradient descent is just now what I was mentioning here is, we will try to adjust the betas by correcting one by one. So correcting one by one means, what I'm saying is, you will try to correct at an individual observation wise. What is that individual observation wise? First, let's take this observation and try to correct what is the best value of beta variant constant by taking the only one value. Are you clear? So that means that, suppose you got the beta 1 and constant is, for example, 0.5 and 2, you got it for only just correcting this one, I mean first observation. And now what I can do, that values will be a starting point for your second observation. And in such a way that what we will do is, the next betas will be corrected in such a way that you will not get the total error for these two observations is high. So that process will continue, one by one observation will get added. Are you able to follow me? Stochastic. Stochastic means, instead of taking the whole error.
Can you explain from the beginning for the stochastic?
Yeah, that's what I'm doing. So what I'm trying to do in the stochastics, I'm going a one by one observation. What I one by one observation, for example, you have 5 records. First, what I will do is, let's take a first record. And you will start with the betas and you will get the error, and the betas will be calculated, whichever gives you the best value, matching with your 300. Are you able to follow me now till now? So I'm taking instead of all the records, I'm taking a single record first. So I finalize my beta value based on single record. Now I will move next record in such a way that the betas will be started from the earlier records. That is nothing but, suppose you finalized my beta 1 equal to 0.9 and C equal to 2. And this will be your starting point, and you will try to adjust the betas in such a way that my first 2 records will be, my first 2 records will give you a minimum sum of squares of error. Are you clear? So here I will add one by one observation like that, so that what happened, your computation of betas will be faster. Make sense? So initially what we are doing is, in a gradient descent, we are taking a random value which is calculating the whole error. Now here what we are doing is, we are taking the first observation and identifying the random value of betas, and we will try to adjust which matches with the first observation y value, and that way I will get the betas. And now that betas will be adjusted along with the second observation, in such a way that my first two records will give you the minimum sum of squares of error. So that way what happened, instead of taking a random value, we are taking as a, in the second observation, you are taking as a initial, I mean, whatever the first record you finalize the betas, that will be your adjustment factor. So that way you'll able to process quickly.
So Chandra, in the second observation, the beta will again be changed.
Yes, that's what I said. Okay, so first what I'm doing is assuming that my first record will be like this, and I finalized my beta value. Okay, I mean, I started with assuming that I have a beta 1 equal to, you start with a 2 and a constant equal to 2, but you know, this is, you gave me cost of something like that. For example, 2 into 2, 540 minus, no, 540 plus 2. So this is your 540 to your predicted value. And you got sum of squares of error, that is nothing but 300 minus 542. So whole square, that is you got the error. Now I changed my beta 1 value, okay, beta 1 equal to 1 and the beta c equal to 2, and you got some value. And like this, you continued this process. You finalized, for example, beta 1 equal to 0.85 and 0.85 and a constant equal to 15.2. Suppose this is you finalize. Okay, assuming that this is the final solution with respect to my first observation. This is a iteration 1. Yeah, it's close to, of course, this is assuming that my value close to 320, maybe a 310 I got it. This is the best solution I got it with this solution. Okay, assuming that. Now, iteration 2. The iteration 2 is, now what happened, you will take this value plus you will take the second observation. What is my second observation? This value. Now what I'm saying is, again, we will start the solution from where? We will start the solution from here. And you will continue the process such that your solution is, okay, beta 1 equal to 0.842 and c equal to 15.9. For example, this is your final solution, you got it. And this is the solution for first two records. If I take it, that is the minimum sum of squares of error you got. And this process I can continue further, iteration 3. Now I will include first 3 observations now, and I will start the solution from here. So this is the way you are fine-tuning your betas. So this is what exactly I was calling as a stochastic gradient, guys. So that means that you are stochastic. There is a process, the continuous process. The process is by adding more number of records. Does it make sense? Gradient only, but now you are taking a individual observation wise instead of taking a full data. And there is other one is mini gradient. The mini gradient perspective, we will take, instead of one observation, we will take a group of observation. Okay, instead of taking one observation, take first 10 observations, a sample of observations, and come up with the beta value. And that values will be added to the second group and third group, like that. So instead of one observation, you take a group of observations. So that is what we are calling as a batch wise gradient or a mini gradient. Right? So most commonly is mini gradient, because the reason is, you know, you will approximate beta value in a first batch itself, so that once you complete the, I mean, it will be faster. Instead of taking individual, you are taking that group wise. I mean, there is no difference between SGD versus mini gradient. In SGD, you will take one observation at a time. Here you take a batch wise observation at a time. I mean, this is a many algorithms use, mini gradient, but yes, you can, I mean, simple gradient or mini gradient depends on the size of the data. If the data size is very big, instead of going with the full gradient, it takes a lot of computational time. So you can go with the mini gradient so that in the initial approximation will be quicker. So guys, one important thing in this case is, if my gradient descent algorithm is, suppose if you have cost function like this, cost function is like this, you are able to get a cost value is, this is my minimum value, you will get it. Whatever betas of this one, you will get the minimum value. But some reason my cost function is like this. So I suppose my cost function having some kind of a curve like this. That means that in this case, how many minimas are there? This is one minima, this is one minima, and this is one minima. There are three minimas are there. Out of all the minimas, this is my global minima. Global minima means minimum of minimas. And this is, global maximum. Also, you can say that this is my global maximum. So, but these are all we call it as local minimas. This is a global minimum. Suppose the solution, when we are trying to identify, we always try to get the optimal solution, means that is a global minima. But what happened is, whenever you are solving the solution, suppose your beta started from here, initial beta, you will able to achieve this solution. But your beta started somewhere here. I mean, random value you start from here. Then you will try to achieve the local minima solution, because it's always look at the gradient descent. So indirectly what I'm saying is, gradient descent will converge the solution to local solution, a local minimum. Gradient descent, any kind of a form, descent algorithm converges to local or global, depends on where the beta value starts. And depends on the cost function. If cost function is have global minima and local minimum, there is a possibility of not getting the optimal solution. What do you mean optimal solution? Global minimum. Suppose a function you have a multiple minimas, right? So, but in our case, in the minimizing sum of squares of error, linear regression, your cost function is what? Polynomial function, right? Polynomial of order 2. So this always have a global minimum, this cost function. But whereas cost functions like, assuming that the cost functions like ANN, that is not a polynomial of order 2. It's a polynomial of any kind of thing. It can be n. So that's the kind of situation. You may have a global minima as well as a local minimas. They are possible. So if I take global minima, local minimas, so that means that based on the beta value, you may get a local solution or a global solution. So that's the reason if you run ANN, I mean, if you run now, if you run after some time, if you don't use the seed value, there is a possibility to get a different solutions. Why? There is a possibility of different global minimas might have existed, sorry, local minimas existed. So you may tend to, or you may need to converge to the solution which is the closest to the beta. Are you clear what I'm saying? So that is also some kind of a challenge you have it with the gradient descent. Gradient descent may not converge to the optimal solution if you have a multiple minimas in your cost function. If you have a less number of, if you have a global minima, then definitely it will reach to the global minimum only. Just like in a linear regression, you have a global minimum. Right? So SVM, you have a global minimum. And like linear, logistic, most of your linear models or a GLM, etc., you have a global minimas. But whereas ANN, you may converge to local minima. See, any kind of a functional form, you can write a curve, you can form a curve, right? So assuming that cost function is one curve, the curve have, suppose like this. This is a typically, whenever you have a polynomial function with order 2, this is the kind of a form you will get it. So in this case, how many minimas you can exist? Only one minima exists, right? This is the place, this is the minimum value. But suppose some cost functions are giving, values, cost function, what is that? We call it as a curve. Suppose this is a cost function for a different algorithm, algorithm, like for example, ANN. So this is a linear regression. For example, ANN, you got the cost function. The cost function looks like this in terms of the curve. So in this case, you have some minimas. You have, how many minimas you have? 4 minimas. This is a one minima, and this is a one minima, and this is a one minima, and this is a one minima. Out of all, which minima is global? Probably, this is the global minima. Global minima means minima's least minimum. Compared to these three, you have a least minimum in here. So that's what global minimum. So my cost function, whichever gives you minimum value, that is, whichever betas gives you a minimum value, that is what my best solution. So I mean to say that whichever betas gives me, this is the minimum value, that is my best solution.
There are many classes.
You can, that is one of them is global, right? You never have, generally you never have minimas is, two minimas is same. Even if you have two minimas is same, you can achieve one of the solution. Either one of them you can take it. So ideally, this is my best solution. But if I apply gradient descent algorithm, what happens? Suppose your beta started here, initial beta is started here, you will converge to this solution. Suppose your beta started here, there is a beta is started here, then you will converge to this solution. And if your beta started here, you will converge to this solution. Right?
Chandra,
Yeah.
yeah, just you told that whenever the position, the beta started, the next minimum value you can, we can consider.
To that. Yes, exactly.
Yeah. So suppose in the first, if I talk about the global minima, here is the first one is the global minima. So how my beta value start on different position? My beta value start from the global minima. Then only my curve will make like that. Otherwise, how can we get the global minima?
That's what I said. Wherever your cost function having a multiple minimas, with the help of gradient descent algorithm, you will not able to achieve the exact solution. Optimal solution. There is a possibility that you will converge to local solution also. So that's the reason I'm saying that if I run ANN with a gradient descent algorithm, if I run by me and if I run by you, if I run by someone, you may get a different solutions. But whereas a linear regression, if you run by you or run by me, run by someone on the same data, you will get the same solution. Are you clear?
Yes, but suppose my beta starts from the two position. Is it possible?
That's possible. So that's what exactly I'm saying, that you may get this as a final solution, or this as a final solution, or this as a final solution, or this as a final solution, depends on where your beta is started. So that means that I'm saying that you build a model, you may get this as my solution. and you may get this as a solution, or this as a solution, or this as a solution. That means that you cannot guarantee that whatever the solution you got it, that is the minimum. That is an optimal. You cannot say that. So this is the place what generally we do is we will run multiple iterations. I mean, I will build the model now and after some time, suppose if I run 4 iterations, I mean, if I'm getting a similar kind of beta values, that means that, sorry, similar kind of outputs, that means that you don't see any significant difference. That means it having only one global. So otherwise, whichever solution gives me a minimum cost function, probably I will choose after multiple iterations.
Okay.
Right. So, but if I'm using a gradient descent algorithm, you may there is a possibility that you may converge to local solution. It's not necessary that you always reach the global solution.
Chandra, in that case, I may not get the optimum results using AI.
Exactly. That's what I said. You may not get the optimum results. So that's the reason what I suggest you to do is you need to convert, I mean, you need to run multiple iterations and look at.
And Chandra, how are you saying that in SVM and linear logistic regression, we will reach a global minima?
That's what I said. There you don't have a multiple minimas. You have only one minimum.
Okay, is this a standard rule? I mean, I'm trying to...
The cost function is like that. For example, my cost function for linear regression is basically what my cost function is. It's always minimizing sum of squares of error, right? Yes or no?
Yes. So it's kind of an exponential, right? So that's what you're saying.
Exponential. Minimizing sum of squares of error, it is a polynomial of order 2.
Yeah. Sorry.
The polynomial of order 2, the cost function, the order, I mean, any polynomial with order 2, you will always have a curve is something like this. If you have a curve is like this, you always have a one minimum only. So what I'm saying is for a SVM and linear and logistic or any generalized linear models will have only one global optimal minimum. I mean, that is one minimum. You will not, the cost functions, you will not have so many minimas. Are you clear? Okay, so now you're clear what is the gradient descent, stochastic gradient descent, what is the mini gradient, and how the gradient descent help you to get the solution. It depends on the cost function also. You may converge to local, you converge to global, right? Okay, now I want to talk about MLE. What is MLE? Maximum likelihood estimator. What is likelihood estimator? So basically, this is something like this. One second. Okay, so guys, this is something what I was saying is the maximum likelihood estimation is something. Let's understand this part. Suppose the method of least square, just now I discussed, right? But this method of least square will assuming that your residuals follows a normal distribution. The residuals follows normal distribution. If the residuals are following normal distribution, then only this minimizing sum of squares of error will works well. If that is not the case, you know, if instead of normal distribution, if it is something follows another distribution, and that's the kind of scenario, the maximum likelihood estimation is works well. So that means that it can be applied models with any probability distribution. So what I mean to say that when will you get minimizing, I mean, normal distribution, I mean, your errors follows normal distribution, your y follows normal distribution, your errors are follows normal distribution. But if y is not following a normal distribution, like for example, y is following some other distribution, and that is the kind of scenario, like for example, in a logistic regression, what is your y variable? It's a categorical variable. If it is a categorical variable, you cannot use, you know, the y is not following a normal distribution, you cannot use a normal distribution, right? So that's the place the MLE comes into the picture, right? So what is this MLE is something like this. So let's understand this one. So basically, let me explain that. Suppose you have y, of course you have x variables, you know, for example, any kind of a classification problem, what you have your y, your x and your y is you are having, okay, for example, customer ID, you know, 1, 2, 3, and you have 1, 0, 0, 0, 1, 1, 1, 0, 0, 0, and you also get a probability of y equal to 1 and the probability of y equal to 0. That is nothing but what? 1 minus of probability of y equal to 1. Correct? Okay, so you got as a 0.3, 0.4, 0.2, 0.1, 0.7, 0.6, okay, so assuming that this is your y and this is your probability of y. So what is your 1 minus of probability of y? This is your 1 minus of probability of y. So what is this likelihood? Likelihood is nothing but a summation of this multiplied with this. So that means that probability of y equal to 1 multiplied with probability of y equal to 0. So what does that mean? So this is a likelihood. The likelihood is this multiplied with this, and you will get the sum of this. This is what we get the likelihood. Okay, this is what we call it as a likelihood. And what we are trying to do, we are maximizing this likelihood. Maximizing likelihood. Okay, so that is nothing but what? Suppose this is the solution you got for some, assuming that beta 1 equal to 1 and constant equal to 2. Based on that only I can calculate my probabilities. Probabilities what? E power beta 1 x1 plus constant by 1 plus e power beta 1 x1 plus constant. So based on that I can calculate my betas and I can calculate my probabilities. I can calculate my 1 minus probabilities. I can calculate the likelihood. So now if I change my betas, instead of 1, if I take a 1.2 and take 2.5, if I change this one, I will get a different probabilities. Will I get different probabilities or not? I will get the different probabilities, and that probabilities I can also calculate the likelihood. And suppose if this is giving me high likelihood, can I say that, this is giving, for example, likelihood is 1.9. Suppose this solution is giving me 1.9, assuming that. Then this solution will be a best solution for me. Correct or not? So that is what maximizing the likelihood means. Now, what is this maximizing likelihood will be same as minimizing the likelihood, minimizing the minus likelihood. Maximize is same as a minimizing of opposite value. Correct or not? And when we are taking the likelihood, it can have a positive value, it can have a negative value. So what generally we do, I mean, it's always a positive value because you will get it's a probabilities, and the probabilities will be very small. So generally what we can take is, I mean, you want to take as a negative and positive, it's always a, instead of taking a simple likelihood, if you take a log likelihood, the solution convergence will be faster. So what generally we do is, what log likelihood is, so instead of taking a 1.8, 1.78, log likelihood will be log of, and of course base is, for example, I think in the base is E only. E is, you don't have E here. I think 3 point, whatever it is, base, I mean log of this one, that is by default it take a leg. So this value will be, of course, if this value is higher, this value, suppose 1.78, my log likelihood is this one, you got it. If this value is higher, I can get this value also higher compared to this. If this is higher than this one, my log likelihood is higher than this one. So instead of maximizing likelihood, I can also maximizing log likelihood. So that means that minimizing minus log likelihood. Correct or not? So indirectly what I'm saying is the minimizing minus log likelihood. Why I'm taking, why not maximizing? You can take it. So if I want to take this one, I can use gradient ascent algorithm. You remember maximization problems, we use gradient ascent. Minimization problem is we use gradient descent algorithms. Do you agree with me? So to maintain the consistency, we always try to converge our maximization problems into minimization problems. Your maximization problems into minimization problems. Now the question is the likelihood, if it is a binomial distribution, your likelihood is this manner. If it is a multinomial distribution, the likelihood calculation will be a different. So how did you achieve this binomial? How did you achieve is, if you remember this PDF function, what is the PDF function for Bernoulli distribution? P power Q. I mean, I don't know whether you remember us. There, the binomial function, I mean, probability density function is P power Q multiplied with 1 minus P whole power 1 minus Q. So anyway, it doesn't remember. This is the binomial distribution based on, I mean, this is your P power X multiplied with 1 minus of P power total number of observations power total number of observation minus X. So basically, end of the day, what we are trying to do is, this is based on the probability density function. So based on the probability density function, your likelihood will be calculated. Okay, so how this likelihood is changing? Based on the distribution of your Y variable. If the distribution of Y variable, if the distribution is satisfying a binomial distribution or a Bernoulli distribution, you have one PDF. Based on the PDF, you will calculate the likelihood. And if the a different distribution, suppose if it's Poisson distribution, you have it. Poisson distribution will have a different PDF probability density function. Based on the probability density function, you will calculate the likelihood. So end of the day, what we are trying to do is, we are trying to maximize the likelihood. We are trying to maximize the likelihood, and that is same as a, you are maximizing the log likelihood. That is same as a minimizing minus log likelihood. Correct? So indirectly we are trying to achieve a solution which gives me a minimum likelihood, minimum log minus log likelihood value, that is your best solution. So how can you achieve? Again, it's indirectly we are saying the gradient descent algorithm. There is no difference in the algorithm perspective. Only definition we are changing is, instead of maximizing likelihood, we are taking a minimizing minus likelihood. That is same as a, that's the reason we always calculate minus LL. What is minus LL? Log likelihood.
Chandra, Chandra, I have a question.
Yeah.
So how are you saying that? So I understand you want to maximize the likelihood. Then we said it can be also equivalent to maximizing log likelihood. That's fine. But how is it equivalent to minimizing minus of log likelihood? I mean, okay, so you're saying negative value you want to.
The opposite is, for example, if you're taking a function like this, this is assuming that my cost function of log likelihood, and exactly this will be the same as a minus log likelihood. The function will reverse. So the same thing, you are getting the value. This is a log likelihood, assuming that this is a minus log likelihood. So the function will reverse. So this is same as a minimizing this value will be same as a maximizing this value, or vice versa.
Okay.
Am I correct or not?
Yeah, and what exactly you meant in the PDF function? I mean,
so basically, this is a Bayesian statistics you need to calculate. There is a difference between probability versus likelihood. So the likelihood is something, if you remember the naive Bayes calculation, we have done it. What is the naive Bayes we did? You remember? In the naive Bayes, what did we do? Posterior probability and prior probabilities. What is the posterior probability? We got it. Probability of y given class, y equal to 1. Sorry, not y equal to 1. Probability of y, class equal to given x, right? If a class equal to 1, given that class, x is same as a probability of x given c1, c equal to 1, and multiplied with probability of x given c equal x1. In this case, x is nothing but x1, c equal to 1, multiplied with probability of x2 given c equal to 1, and so on, and of course multiplied with probability of c equal to 1 divided by probability of x, where x is nothing but x1, x2, x3 values. So if you remember, the left side one we call it as a likelihood, and the right side we call it as a prior probabilities. These are probabilities. These are prior probabilities. So in a similar lines, if you think about it, the likelihood for probability of c equal to 1, you got it, and similarly probability of c equal to 0 also I could get it. So this is same as what a probability of x1 given c equal to 1, probability of x2 equal to given c equal to, so that is nothing but, if I want to get my maximization, is nothing but you are multiplying with these, where I'm able to see the differentiation between zeros and ones. Right? So based on, of course, the entire theory is developed based on this one. So for the time being, since you are not aware of the probability density functions for each formula, etc., that's how you will get a little bit different. But if you understand at least a Bernoulli distribution, a Bernoulli distribution is something is what, for example, you have your y variable 1 and 0. So that is nothing but you are calculating the probability for 1 and probability for 0. So that means that you will get the probability values for 1 and 0 will be the same. And that is same as a probability of data given P. That is nothing but how many ones are there? 6 ones are there, and 4 zeros are there. So then your total likelihood will be p power 6 multiplied with 1 minus p power 4. So of course, when you have this kind of a probability density function, I mean, this is exactly we call it as a likelihood. This is the probability density function for what? Bernoulli distribution. This is exactly the same as a likelihood for the given y variable. So instead of taking a likelihood, we are taking a log of likelihood, because what happened is there you will, if here you will get a product, when you're taking log, you will get a summation. So when you have a summation, it's very easy to get the optimization value quickly. So that's the reason, to simplify the processing perspective, we take a log. Does that make sense? So this is what exactly I'm saying, that if I'm taking this one, this is what exactly I'm saying, for what values of the p and 1 minus p you will get it, so that you will get the maximum value. So that's how you will find out the parameters, whichever parameters, I mean, for example, my 0.6 is my p value, but what values of 0.6 I'm getting this p value, that is what we are trying to estimate that. So of course, here I simplified the process with the Bernoulli distribution. But if the distribution is a Poisson distribution, or the distribution is normal distribution, if the distribution is some other distribution, the likelihood values, I mean, this function will change. But what I'm saying is, you can apply to any distribution. So that's the reason in generalized linear models, generalized linear models is, I told you generalized linear models means your y can be any distribution. So that's the place you cannot use minimizing sum of squares of error. What we are trying to use, you are maximizing likelihood or minimizing the minus likelihood. So that's the reason we use in a generalized linear models, we use MLE. So you can say that linear regression is one special case of generalized linear models. So for linear regression, you can use MSE, minimizing sum of squares of error, or maximizing likelihood. So for linear regression, you can use any of these methods. But whereas a logistic regression or any other models, you cannot use sum of squares of error. There you have to use maximum likelihood estimation. Right? Other regression models, you have to use MLE. You cannot use minimize sum of squares of error. The reason is their errors will not follow a normal distribution. So now you understand underlying the concept of what is MLE, what is minimizing sum of squares of error, what situation we use MLE, what situation we use MSE, and what is the likelihood, what is the log likelihood, what is a negative log likelihood, etc. Now, one important thing you need to understand is, if I increasing the x variables, there is a possibility of reduce minus log likelihood value, or it will get stagnant, Okay, so that means that by increasing the value, by increasing more number of x variables, there is a possibility of reducing the log likelihood. That means that you will get more accuracy. Okay, so but what I'm trying to say is, by increasing x variables, you are just seeing a very minimal likelihood, very minimum improvement in the likelihood. Suppose you got as a x1, x2, x3, suppose x4, 4 variables you have it. You have 4 variables. You got minus log likelihood value is, you got as a minus 320, for example. And by increasing x1, one more variable I added, x4 and x5. Okay, this is x3, no. Suppose here I'm able to increase, I'm able to reduce, for example, 321. And adding one more variable to here, and I'm able to see very less improvement, minus 321.01. So adding x5 variable, it's okay. You are seeing some kind of improvement or some minimum value in my log likelihood. But adding one more variable, is it really improving your log likelihood? It's very hardly anything. So that means that the x6 variable is not important variable. Can I say that? So, but by increasing this one, if I'm looking at a simple solution, I will look at the all the variables. I will get the minus 321.1. So I can say that this is my best solution. But if I compare with this to this, you hardly see any improvement. Okay, this is the best solution, no doubt at all. But by adding one more variable, you also get some kind of problems in your problem. What is the problem you will get by adding one more variable? Adding variables to model. What is the problem you will get it? It will overfit the model, right? You remember, it will increase the complexity, it will overfit the model. So that means by adding unnecessary variables, by adding a variable which is contributing minimum value, that will not be helpful. So that is the place we will not look at log likelihood as something. This is the place we use, there is a function called AIC. AIC is nothing but function of minus log likelihood and number of variables you are using it. So what indirectly I'm saying that is, if my AIC value is penalizing, what is the contribution you are getting? Suppose if from here to here, for example, my AIC value you are getting as a, for example, 20, for example, and here you will get minus 20.05, but here minus 19.5 you will get it. The reason is, what you are doing is you are penalizing your log likelihood if the contribution from the new variable is getting added. So that means that which solution is best solution in this case? This solution is best solution. That means by adding one more variable, if you are not significantly impacting your log likelihood, at that time you will not able to get the best minimum AIC value. So that's the reason, instead of using minus log likelihood, we use AIC value. I mean, instead of minimizing minus log likelihood, what we do is minimizing AIC value. Are you clear? So this is the, if you remember, a lot of scenario we are looking at the AIC value. I think even in the forecasting and some places I seen that AIC value. Why did I look at AIC value? This is the reason. Now you are able to relate the previous steps, what we discussed. Good guys. So see, this is exactly I want to talk about.
Chandra,
yeah.
So Chandra, in this case, the output will be minus 19.5, right?
Correct. So not minus 19.5. I will, if I'm using a minimum AIC value, I will get this as a solution, right?
Okay, okay.
Because
Yeah.
20.05 is
Yeah.
If I'm using a log likelihood, yes, this is the solution, you will get it. But if I'm using a minus log, AIC value, yes, I will get the solution.
Okay, and AIC will penalize minus log likelihood if there's no significance in
Variable,
adding
yes.
the variable. Okay.
Exactly. So that's the reason, instead of using a minus log likelihood, generally we prefer to use AIC value. But end of the day, AIC is nothing but what? It's a function of log likelihood and number of variables you are using it. Perfect, guys. So with this thing, I think most of your concepts is done. Only thing is I left with exercise. I thought of finish it today, but I know it's a little difficult to, I think in the next class, probably first half an hour, I will explain with the case study. And then we will move to the, what is that? text mining. So in the next week, probably the exercise either me will take or maybe Sunit will take, and he will, if I'm taking exercise, I will take a first half an hour, and then I will hand it over to the Sunit, or Sunit will continuously take this part along with the exercise. First he will finish the exercise, and then he will continue with the the text mining part. Is that clear? I think the conceptually there is no doubt. Only thing is the implementation time. The implementation place, I think if you are familiar with the decision trees or ensemble learning, whatever we discussed, the concept is exactly the same. Only thing is you need to identify what is the function and what are the tuning parameters. That's all. And you need to understand what are the tuning parameters, etc. That's all. There is no change in the methodology. Yes, Prerna, you have any questions?
Yeah, Chandra, can you go back to the MLE slide you were showing, Chandra? Just one quick question. So, Chandra, can you please explain what the table, so what is the table on the left? This is the actual Y value.
I was saying that this is my Y value. If I'm calculating the probability, my probability value will be my probability of Y equal to 1 and probability of Y equal to 0 I need to calculate. So assuming that probability of Y equal to 1 P and probability of Y equal to 0 is 1 minus P, my likelihood of this value will be this one.
Okay, so I am expecting P to the power of 6 because there are 6 ones.
6 ones and 4 zeros.
Okay, so this would be my log likelihood.
This is likelihood.
This is likelihood, yes.
Yes.
Okay, that's it. Thank you.
Yeah. Perfect, guys. So let's meet next week then. Thank you so much.